So, the score that we would predict for any individual is simply the mean of the group that they're a member of. And so this y hat ij is simply the estimated grand mean plus that treatment offset. Remember, we're simply decomposing our group means into a sum of the estimated grand mean plus the difference from that grand mean. So our residuals in the model, the E sub ij's, are simply those differences. The differences between what we actually observed for a person and what we would predict for our person. But let's remember, our prediction for a person is simply the sum of those two components, the y bar plus the t sub j. Now let's look at these residuals on our plot, because they're going to be pretty familiar. They're simply, within each group, the differences we had between those people and their actual group mean. How much individuals revolve or vary around their own group average. Like I did before, let's switch the axis here and put these out horizontally. So here again, I've centered the residuals, that is, subtracted off an individual score from the own group mean, and now we have residuals centered at 0. Now remember, in a population, when we actually saw the population data, we would know whether the variances or standard deviations of these different residual groups would be identical. For a sample model, we're going to have to assume that these distributions have the same variance in the population. And by saying that, what I mean is, in the population, how spread out individuals are relative to their group doesn't depend on which group they're a member of. Now, this is an assumption we'll have to check on the basis of our sample data. It may not always be true. It could be that everybody on Delta paid nearly the same amount, an amount that could be different than the other groups, but within the group of Delta, it could be that individuals paid nearly the same. Whereas on Southwest and Virgin, it could be that people in each of those groups spread out pretty widely. Now that, again, is going to be something we'll check on the basis of our sample. But for now, we'll assume that this assumption is correct, that the variance in these different groups in the population is actually the same. And that's why those S-squareds, the variances of our residuals, do not have a subscript. We'll be assuming that we're trying to estimate one unified variance in the population. And the reason this is useful is that all of these data are now useful for us to estimate that one population variance. Now let's remember how we calculate variances. If I go back to the slide I showed you before, we're dealing with sample data, and so we'll be taking sums of squares. In this case, we'll have y's and not x's, but then we'll have our sums of squares divided by the number of individuals minus 1. Now let's talk about that n minus 1 for a second. I didn't show you this before, but n minus 1 here is actually referring to a specific quantity. It's called the degrees of freedom of that statistic. Now, don't get lost in degrees of freedom yet. We'll come back to looking at degrees of freedom and what they really represent. But degrees of freedom for now is just a measurement of how much useful information we have on which to estimate that population variance. So we'll be using a formula like this. We'll find sums of squares for those residuals and divide those sums of squares by their degrees of freedom. And that will give us our best unbiased estimate of the population sigma squared, that one sigma squared we think describes all those different groups. Now, before I show you the formula for the sums of squares across all the different groups, let's remember how many groups we have. We're actually taking the sums of squares within each group and then summing those separate sums of squares. And so our formula will actually have a notation you probably haven't seen before, 2 summation operators. Before I show this to you, remember that all formulas are simply instructions on how to operate on data. So even though this formula will look complex, it's really describing a simple series of operations that will get us the sums of squares. So here's the formula for the sums of squares for air. And let's talk about first the interior component, and then we'll come back to these double summation operators. First, the interior component. This reads off as the individual score, so the yij, minus the prediction for the yij, so for that person. Remember, the prediction for any person is simply the group mean that they're a member of. So if we consider Tom, who flew on Delta, this interior component says take Tom's cost of flight minus the prediction for Tom's cost of flight, which is simply the mean for the Delta group. And then we'll square that observation to get one squared deviate. Now, the summation operators here are simply a set of instructions. The first one we evaluate first. So, for every individual in the delta group, every I in the delta group will perform this operation. Then we go out to the outer subscript and actually increment it 1. So j is no longer 1, but 2. So for every individual in the Southwest group, we'll do the same operation. Then finally, for every individual in the Virgin America group, we'll do the same operation. Another way to write this, which is perhaps a little bit simpler, is simply representing this interior component in terms of the residual. That is, the yij minus the y hat ij is always just an eij. So we can write this formula as the sum over all groups, over all individuals, of the residuals squared. And this gives us the sums of squares for those residuals. But remember, we're going to be using these sums of squares to estimate a variance. And we find variances by dividing sums of squares by their degrees of freedom. And the way to do this is simply dividing sums of squares for error divided by degrees of freedom for error. And this will yield us a quantity known as the mean squared error. Remember, variances are also called mean squares. They literally are the mean squared error of individuals. In this case, the mean squared error is the mean of the squared error of each individual. Another way you'll see this written is s squared with a p, and that refers to pooling. Pooling is just a type of averaging. It's simply taking the sums of squares within each group, adding them up, and dividing by the total amount of independent information, and that is just the degrees of freedom. And for us, the mean squared error is our best unbiased estimator of the variance in the population. And remember what that represents. When we saw the population data, we actually saw that people did vary around their groups. And so the mean squared error in our sample is our best guess of that variance in the population, how much individuals are differing from their group averages. And importantly for us, that mean squared error, the thing we find from the EIJs, is going to be our benchmark of error. It'll be the thing that helps us understand whether the T sub j's are actually large relative to what we would expect by chance, or small relative to what we would expect by chance. Just like we've seen all along, variability gives us insight into how much we should expect our sample statistics to deviate from the population parameters. And by forming this sample model, we're importantly trying to find out whether those T sub j's are actually there in the population. That is, we'll always get T sub j's that are a little bit different from 0, but we want to know whether those differences are reasonably attributable to chance, or whether they're not reasonably attributable to chance. If they're not, then we actually have some statistical reason to infer that the population actually uses the grouping variable we prescribed.